Hello everyone, hope that you are well. This lesson is going to cover carboxylic acids. We're going to do a quick quiz of and then we're going to begin to talk about the concept of fractional distillation. So of the organic chemistry section, C6.2, we're going to cover lessons 4 and 5 in this. Okay, so last lesson we talked about alkanes, alkenes, and alcohols. And we talked about each of their key features. So for example, you should remember that alkanes and alkenes are both examples of hydrocarbons because they contain carbon and hydrogen only. And alkanes had a general formula CnH2n plus 2, and alkenes had a general formula of CnH2n. We talked about the fact that alkanes are saturated molecules because they contain the maximum number of hydrogens because they only contain single covalent bonds, where alkenes contain a double bond and therefore are unsaturated. We talked about the test for unsaturation being we use bromine water and that will decolorize from its normal orangey brown solution to colourless in the presence of an alkene or an unsaturated molecule. And then we talked about the main reaction of alkanes as combustion. So we talked about how we have complete and incomplete combustion. Complete combustion, we have our fuel, oxygen, and we produce carbon dioxide and water. And in incomplete combustion, because we have a lack of oxygen, we get carbon monoxide, and water. We then introduced the idea of alcohols. So we talked about alcohols containing a hydroxyl group, which is that they contain an OH group. And they had the general formula that was CnH2n plus 1 OH. We said that they were not hydrocarbons because they now contain oxygen. And we actually focused in our study of alcohols mostly on comparing the two main methods of manufacture, which were fermentation and hydration of ethene. Both methods you should be able to compare and discuss. Another reaction of alcohols I just want to mention that we can do is we can combust them in the same way that we can combust alkanes. And that sort of brought us to the end of our introduction to the 3 functional groups. I want to recap what we meant by a functional group. So a functional group was a organic molecule that has a general formula that increases with carbon chain length in a regular way and has a unique feature. So in the case of alkanes, it's that they're saturated. In the case of alkenes, it's that they're unsaturated, they had a double bond. And in the case of alcohols, they had a hydroxyl group, they had an OH. And that made those weakly acidic. The other thing that we talked about is we talked about that we need to know the names for the different chain lengths of the molecules up to really up to 10, but for the specification lists explicitly up to 4. And we said the reason is because after that it follows geometric nomenclature. So it uses the same word that you would use for different shapes. So 5 is pent, 6 is hex, and so on. So the simplest alkane we had was methane. Then we had ethane, propane, and butane. And then pentane, hexane, heptane, octane, etc. Alkenes all end in E. Remember, we don't have methane because you can't have a double bond to yourself. So the simplest alkene is ethene, then propene, butene, etc. And then we talked about alcohols all ending in ol. So we have methanol, ethanol, propanol, and butanol. So our 4th functional group that we're going to talk about, which is new for us, is carboxylic acids. You've probably had the information on the screen long enough now to have hopefully noted it down. But if not, now is the time to do so. So carboxylic acids, which is the 4th and final functional group that we're going to talk about for the time being, There are more that you would do in A-level chemistry, but for GCSE, this is where we stop. But they contain two unique groups. They contain a carbonyl group and a hydroxyl group. Well, what does that mean? So what I would suggest that you do is start by drawing the molecule here. You should recognize from the chain length, we've got two carbons. So that means it's going to be F. And this is all carboxylic acids end in oic acid. So this is ethanoic acid, okay? Or vinegar, as it's also commonly known. So ethanoic acid is an acid that we use as our standard example of a weak acid. And carboxylic acids are all weak acids, which we'll talk about in a second. Now, when you look at this, I just want you to notice there are three distinct bits. There's the C double bond O. So I would draw like a little dotted red line around that just to sort of separate that out. That is our carbonyl group. So a carbonyl group is a carbon double bonded to an oxygen. Okay. And our hydroxyl group, which we have met before, that's what is the unique feature of an alcohol. So this is the OH. So in exactly the same way that an alcohol has an OH group, so does a carboxylic acid. And then the rest of the molecule is just what we call an alkyl chain. It's just the rest of the carbons and hydrogens, however long that may be. And in the case of carboxylic acids, the carbonyl and hydroxyl are always on the same carbon, and they're always at the end of the chain. So this chain could get as long as we want with a number of carbons, but there's always going to be a carbonyl group and a hydroxyl group at the end. There is nothing to stop you having methanoic acid, where there is no extra carbon here. It's just a hydrogen. That's perfectly fine. And then we have ethanoic, propanoic, butanoic, and so on. All carboxylic acids are weak acids, and that's because the hydrogen here on the hydroxyl group can be dissociated. Remember, the definition of a weak acid is that they partially dissociate. So it's this hydrogen in particular that will split. To put that into perspective, for ethanoic acid, every 1 in 170,000 ethanoic acid molecules will split into an ethanoate ion and a H+ ion. That might not sound like a great deal, 170,000, but if I compare that to water, water has a dissociation value of 1 million. So it is considerably higher than water and therefore considerably more acidic. It has a pH of around about, depending on the concentration, but usually around about 3 to 5. So this is just a ball and stick diagram, just showing the molecule with the red molecules representing the oxygen, just to give you a sense of shape. And the final thing to note from this is you need to know the general formula of carboxylic acids, which follows much the same as an alcohol, apart from the fact that you have what we tend to write the carboxyl group as COOH. And so that indicates that the first oxygen is double bonded to the carbon, and then the OH is then covalently bonded to the carbon as well. So that's the way we typically write it. There would be nothing wrong to use a molecular formula where all the carbons and all the hydrogens were noted together, and all the oxygens, obviously. So in the case of ethanoic acid, I could write it as CH3COOH, or I could also write it as C2H4O2. But the first example is the way we typically write it, just to make it clear that this is a carboxyl group. So that's the basics for carboxylic acids. Now, I'm just like you to pause the video for a second and just have a quick read at this section. This is directly from the textbook, and I'll talk you through this in a minute, just after you've had a quick read of it. Okay, so this is the only other major thing that we need to know about carboxylic acids at this particular point. We will talk a little bit more about them in a couple of future lessons, but at this point, the only other thing that we need to know is how do we make them. So carboxylic acids are formed when we react an alcohol, which we've already talked about, with an oxidizing agent. Because if you compare alcohols and carboxylic acids, they both have a hydroxyl group. The difference is a carboxylic acid has a carbonyl group, which, as we know, is a carbon double bonded to an oxygen. so we need to add more oxygen. Hence, we need an oxidizing agent. So an example of a strong oxidizing agent would be potassium permanganate. Okay, potassium permanganate in solution is usually a dark purple color, which you can see on the left-hand side. And that's because the oxidation state on the manganese is 7, and that gives it its bright purple colour. Now, we can take a simple alcohol, such as ethanol, and add an oxidizing agent, and we will just change the ending of the name. So ethanol will become ethanoic acid. Okay. So just recognize that the chain length has not changed. It's just that we've added an extra functional group. So ethanol would make ethanoic acid. Methanol would make methanoic acid, and so on. By adding the oxidizing agent, the other thing, there's 2 other steps that we need to do. We need to warm it using a water bath. We do this using a water bath as opposed to a Bunsen burner, because ethanol is obviously flammable. And so that would not be a good way of getting it to oxidize in the way that we want. We don't want to burn it, we want it to turn into ethanoic acid. Then we also add a little bit of sulfuric acid so that it's done in acidic conditions, and the result of that is we will then change our alcohol into our carboxylic acid. So we need an oxidizing agent, we need acidic conditions, so we add sulfuric acid and we heat it using a water bath. The colour change that occurs is the potassium permanganate, which is our strong oxidizing agent, will go from purple to very pale pink, almost colourless. So if you look at the diagram on the right, you'll see a very pale pink tinge just at the surface of the solution. It will appear colourless to you in most of the rest of it, but it is a very, very pale pink because of the concentration. If you don't believe me, take my word for it. And we've then made ethanoic acid. So obviously it just mentions in the final paragraph about the risks inherent in this. I've already sort of talked about why do we not use a Bunsen burner. As I've said, ethanol is flammable, and therefore we want to be careful with that. So that's how we make carboxylic acids. We oxidize alcohols. So that brings us to the end of our functional groups. So we're going to do a little quiz now. There's no point for making mistakes or anything like that. There's no downside to this. But I'm going to fire some questions at you. They're going to all be multiple choice. I'm going to give you 10 seconds to have a think about it, and then we'll talk through the answers. Okay, so if you want to pause the video to give yourself more thinking time, that is totally fine. There's only 5 questions, so here we go. Which of the following is a hydrocarbon? Okay, so the first thing you should think about for this question is what's the definition of a hydrocarbon? So the definition is a hydrocarbon contains hydrogen and carbon only, and that word only is important. So let's look at our 4 choices. We've got ethanoic acid, that's a carboxylic acid. Propene, that's an alkene. Butanol and hexanal. Okay, now butanol is an alcohol because it ends in -ol. Now hexanal, let's just focus on that for a second. You'll notice that's an ending we haven't seen before. And it's the -al ending, and that means it's an aldehyde. And since we've not encountered that yet, you can assume that's the wrong answer. And they will do that in exams where they will throw you a curveball that you've never heard of, and don't be too put off by that. So the one that is a hydrocarbon is, of course, B. It's propene, because butanol is an alcohol and therefore contains a hydroxyl group. It's got OH, and ethanoic acid obviously has 2 oxygens in both the carbonyl and the hydroxyl group. Hexanal is basically like a carboxylic acid, but without the alcohol hydroxyl group. It only contains the carbonyl group, but it just has the C double bond O. So that also has oxygen. So the answer is propene. Okay, which of the following homologous series? That should say which of the following is the homologous series for unsaturated hydrocarbons. So what's the general formula for unsaturated hydrocarbons? Okay, so again, this is testing you on two things. One, you have to realise when it says unsaturated hydrocarbons, what group is it talking about? And of course, you should realise that unsaturated means it has a double bond. So it's talking about alkenes. And then you need to recognise from the four options which is the general formula for each option. So A is the general formula for alcohols. B is the general formula for alkanes. C is the general formula for alkenes. And D is the general formula for carboxylic acids. So unsaturated hydrocarbons are alkenes, so it's C is the answer. Which of the following organic molecules could I test for using bromine water, and what type of reaction is this? Okay, so we test bromine water. We use that as the test for unsaturated molecules. We test double bonds. So again, we're looking for an alkene. Of our options, obviously we've got carboxylic acid, an alkene, an alcohol, and an alkane. All the propene, the 3 carbon chain version. So B is our answer based on that. And what type of reaction is it? It's an addition reaction. What that means is the bromine adds to the double bond when it reacts, and that's why it goes from being orangey brown to colourless, because you're adding the bromine to the double bond. That's why the colour disappears. So you should also know that that is an addition reaction. So if you didn't have that in your notes, add that. But B is the correct answer. What is the name of the following molecule? Okay, so there's 2 steps that you need to go through when you get a question like this. The first is you need to count the length of the carbon chain. So we have 4 carbons in this chain, and that's therefore going to make it bute. Okay, so that limits it to B or C. 3 would be if there was, A prop would be if there was 3, and pent would be if there was 5 carbons. The second thing, after you've established the carbon chain length, is you have to identify which functional groups are present. In this case, we have a double bond again. We have an alkene. So all alkenes, the clue is in the name, end in -ene. So this is butene. If it was butanol, that would be an alcohol. If it was pentane, that would be an alkane. And obviously propene would be the same molecule, but with 1 fewer carbon. I would encourage you to have a go at drawing out the other 3 molecules on here just for yourself so that you can picture what they look like. And the last question, which of the following is not a product of incomplete combustion of ethane? So remember, for complete combustion, we have 2 products, water and carbon dioxide. In incomplete combustion, we have 3, water, carbon, and carbon monoxide. So the thing that we don't get in incomplete combustion is carbon dioxide. We get that incomplete. Okay, and that brings us to the end of our little quiz. So I'm just going to introduce in this video the concept of fractional distillation, and then I want you to go and have a look at another video sort of breaking it down and showing you how we would do this practically in the lab. I just want to start with this, which is what's the connection between the images? Well, these are all products that we get from crude oil. So what we need to understand is we get a massive range of products. We've got flammable gas, we've got lubricating oils, petrol, bitumen, which is what's used to make tarmac, which is in the roads, paraffin in candles, grease, literally. And obviously, we then get all of our plastics from this. We get a massive range of products from crude oil. We need to understand how we take crude oil, which is, as the name suggests, is a crude mixture of different hydrocarbons, and how do we separate them? Okay. So when you have a look at the other video, you will see how we do this practically in the lab. So I'm not going to focus on this now. Instead, I just want to focus on the main points of a fractional column. So as I've just said, when we get crude oil out of the ground, we have to separate it out into its fractions. Fractional distillation is one of the separating techniques that you encounter in C2. It's one of the ways that we separate out different liquids of different boiling points. In this case, those are all alkanes. So what we do is we input the alkanes at the bottom of our fractionating column, and we heat them a lot. Some of the chains are so long that even at those high temperatures, they will still be in the liquid state. And those are the heaviest, longest carbon chains. And we're talking about carbon chains of 40 plus, and those will come out as what's called bitumen. Bitumen is used to make roads and is basically used to make tarmac, but is used to make roads and for roofs. As you go up the column, we have a temperature gradient, and as you go up the column, it gets cooler and cooler, and the different molecules, because the chain length gets smaller as you go up, they have a lower boiling point as you go up the fractional column, and so they start to condense at each of the different fractions. So obviously only the ones that are absolutely the largest molecules will still be a liquid even at high temperatures, and they will be at the bottom. But when all the others are injected into the fractional column, they are gases. So they travel up the fractional column, and then as they get to the temperature that they will condense at, they will then condense, and that fraction is then separated out. So the next fraction is fuel oil, and we use that for ships, for factories, and for central heating. After that, we have lubricating oil. We use that for lubrication, for waxes, for polishes, etc. Then we have diesel, which happens at about 270 degrees. And obviously, we use that for diesel fuel. And kerosene, 170 degrees. We use that for jet fuel, for paraffin. Then we have a group of chemicals called naphtha, and that's 120. We use those for chemical stocks, like in the lab. Then we have petrol at about 70 degrees, which we use for petrol. And at the very top, we have refinery gases, which are our bottle gases that come out. So at the very top, we're talking about very short chain hydrocarbons like methane, which we have in our gas taps for Bunsen burners, or butane, which you will probably have if you've got a gas canister for a barbecue, or if you've been to a caravan or something like that. So that's like the general list of fractions as they come out. Now you might think, why am I spending time on that? You do need to know them. So one thing I need you to do from this slide isn't just make some notes on it, but also I'd probably advocate making flashcards, because you need to know the different fractions in order, and you need to know what they're used for, because it can come up. So it's something you will need to spend a little bit of time just trying to commit to memory. But if you work out your own sequence to help you remember it, it's not too difficult. The other general thing you need to know is you need to know what happens to the molecules as we go up the fractionating column. So the larger molecules exit at the bottom, the shorter molecules exit at the top. We just need to compare the small versus the large. So the large molecules, the very long chains, have very high boiling points. The reason for that is because they're a long chain, they have high and strong intermolecular forces. They are very dark in colour, think of the colour of tarmac, and also thinking of tarmac, they're very thick. Also, if you throw a match onto tarmac, it wouldn't catch fire. That's very different to, say, methane at the top of the group. So it's difficult to light, which means it's not volatile. So it's thick, it's viscous, not volatile, very dark in colour, and has a high boiling point. In contrast, the smaller molecules, as you go up the fractional column, the boiling point gets lower. The different gases get easier to light. So obviously lubricating oil doesn't catch fire easily, but can still be efficient in an engine to keep it moving smoothly, hence why we use it. They get lighter in colour as you go. Obviously at the very top, the gases are colourless. They're easy to light, they become more volatile, and whilst they are still liquids, they become runnier as you go up. So petrol is not as thick, for example, as diesel. So those are the general trends and patterns that you need to be aware of. So really, for fractional distillation at this stage, you need to make sure you've taken notes on this slide, put it into a format that you are happy with, and that you can recall the key information. I'm just going to quickly address these questions. Okay, how does it separate crude oil into fractions? And just give you a quick summary. So crude oil is heated at the bottom of the fractionating column. It has a temperature gradient. It's cold at the top and hot at the bottom. The fractions obtained are mixtures of the different hydrocarbons. They are separated out because they have similar boiling points, and the low boiling points exit at the top and the high boiling points exit at the bottom. And in terms of how this works, the key idea for you to understand is the idea of intermolecular forces. So hydrocarbon molecules are joined together by covalent bonds, but between those chain molecules you have intermolecular forces. The intermolecular force is the thing that's broken, not the covalent bonds when it forms a vapor. The larger the hydrocarbon molecule, the stronger the intermolecular force is, and therefore the higher the boiling point. So bitumen, which is a very long-chain molecule, C40, has a lot of intermolecular forces. That's why it's so thick. That's why it's difficult to light and very dark and has such a high boiling point. And in contrast, small chain hydrocarbons are gases. They are they have very low intermolecular forces. Okay, so that explains fractional distillation. So make sure that you've added that to your notes. Next time we're going to look at cracking, which will build again on what we've covered today. So if you've got any questions, please feel free to ask, and I will see you next time.